Hey everyone, Morgan here. So we're on page 11 of the Light and Quantum Mechanics outline for AP Chem, and we are talking about the Aufbau Principle. Now, this is a German term. Auf is basically up and Bau is building. So, the intended purpose of this term is the building up principle of electrons going into orbitals. Now, if you take a literal translation of the word as it's used today, Aufbau would actually mean construction. Okay, the building of new structures. Okay, and to add an E on the end of it would make it more the building up. But this is the way that it's been done since, I think, the 1930s, so it's not going to change. The building up principle. Now, when you look at this chart, which is an Aufbau chart, it is a plot of energy going up. And each of these circles represents an individual orbital in its shell and subshell. The lowest energy, this is the low energy, is the 1s orbital. And that's where electrons are going to go before they go anywhere else. And then they're going to go into the next highest energy level and work the way up this chart. Now, this chart also maps out what is our current periodic table structure. The 1s, 2s, 3s, all of these s's are are groups 1 and 2 on the periodic table. The p's are the groups over there 13 to 18. The D's are in the middle, what we call the transition elements. The F's represent the lanthanides and the actinides. Okay, so it's a slightly different way of looking at the table, but it tells you what its structure is. And for that reason, you don't really need to memorize this table. It's not that important. Okay, now, electrons will go into low energy orbitals first. Okay, and when they do, they're going to follow something that is called Huns Rule, named after Frederick Hunt. And Huns Rule states electrons will singly occupy orbitals before they doubly occupy orbitals. Now that is something that's very easy to understand when you see it in action, and maybe not the easiest thing to understand based upon these words. So let's see this go into action on the next page, and I'm going to keep this handy just in case I need it. And I have pre-printed for you here what looks like an orbital chart like this Aufbau chart right here. So it's easy for us to put electrons in. We'll do the elements in order up to number 25, okay, beginning with hydrogen, atomic number 1, which means it has 1 electron. We represent that electron by putting an arrow into the 1s orbital. No, electrons don't look like arrows. Okay, but it's our way of representing them. Okay, this one is called spin up based upon the 4th quantum number, which we talked about previously. Now for helium, 2 electrons, spin up and spin down. It is less energy required to spin an electron here than it is to put it up here in the 2s orbital. Okay, so it will spin before it goes up. In the case of lithium, 3 electrons, spin up, spin down, and the next one will go into the 2s orbital, because you can't put a 3rd electron into that orbital. For beryllium, spin up, spin down, spin up, spin down. Now, boron, we're going to need the 2p orbital, which is slightly higher energy than the 2s orbital. And in fact, there are 3 2p orbitals. So we have the 2s subshell and we have the 2p subshell, okay, of this second energy level. And there are 3 identical 2p orbitals that have the same energy. The technical term for that is they are degenerate. So a spin up, a spin down, a spin up, a spin down, and a spin up. And everything that I've shown you here so far is called the Aufbau Principle, the building up. For carbon, you're going to see Huns Rule. Spin up, spin down, spin up, spin down, spin up, spin up. That is what Huns Rule means. They are going to spread out in the degenerate orbitals, the orbitals of the same energy, before they spin. So for nitrogen, spin up, spin down, spin up, spin down, spin up, spin up, spin up. Now, for oxygen, rather than the next electron going up to the 3s, which is considerably higher in energy, you'll notice here, going from 2p to 3s, they'll spin. Spin up, spin down, spin up, spin down, spin up, spin up, spin up. That's 7, and number 8 goes like that. And this is a really important configuration, big time important. It's going to have a lot of implications for what happens next in the chapter. Spin up, spin down, spin up, spin down, spin up, 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 down, and down. See, the thing is, you're very unlikely to have to draw one of these on an AP exam or even on one of my tests, but you are guaranteed to have to answer a lot of questions based upon them. Now, neon, spin up, spin down, spin up, spin down, spin up, 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 and then down, down, down. And what you're going to notice here is that helium and neon are both noble gases, and they both have completely filled valence shells. Their outermost shell, the 1s is the outermost here, and the 2s and 2p are the outermost here. Those are completely full, which means they are very stable. Okay? There is no room to add any more electrons without them having to go up to the 3s orbital, which requires a considerable amount of energy to happen. Okay? And that gives them some inherent stability. For sodium, spin up, spin down, spin up, spin down, spin up, 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 down, 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 and a spin up in the 3s. For magnesium, up, down, 3 up, 3 down. Sounds like the end of an inning in baseball or a sergeant in the army. Aluminum. Now, aluminum has an interesting position on the periodic table. It's directly beneath boron, isn't it? So spin up, spin down, spin up, spin down, up, 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 down, 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 up, down, and up. So what we're seeing here is the electron configuration is going to determine an element's position in the periodic table. All right, for silicon, we have an up, down, 3 up, 3 down, an up, down, and then 2 up. And I want to point out that that, okay, is like carbon, and silicon is beneath carbon in the periodic table. For phosphorus, it looks like this. Phosphorus is directly beneath nitrogen, and there are some very similar chemical properties, especially when it comes to bonding. Sulfur. Now this one has a lot of implications because it is right beneath oxygen. And it's got that doubly paired electron in the 3p, the way that oxygen had a doubly paired in the 2p. Similar behaviors. It's going to be very important when we talk about periodic properties. For chlorine, what we're seeing here is it's going to have a similar valence electron configuration to fluorine. And argon, which is a noble gas, is going to have completely filled outermost orbitals. I hope you're noticing that when I'm doing these, even though I know that 3p is going to be full, I still go up, 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 down, down, down. Potassium, an alkali metal, like sodium, like lithium, is going to have one valence electron in the 4s, which is why it is so very reactive. Calcium, now, things are going to get a little bit different at this point. We are dealing with transition metals. And on our chart, okay, what's going to happen is we go from 3s to 3p to 4s. And then you're going to notice that the 3d is lower energy than the 4p. So the 3d will fill before the 4p, which seems a little weird. But that's the way the quantum numbers work out, like that. Titanium, we see something very similar. Following the same pattern that we would expect. Vanadium. Three up in the 3p, 3 down in the 3p, up, down, up, up, up. Now, another thing that we know that happens in nature, but we just weren't expecting. Chromium is just an exception to the rule. Spin up, spin down, spin up, spin down. 3 up, 3 down, up, down, up, 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 down, down, down. Now, what we see here is up and then 5 that are up. Call this guy a rebel. One of the electrons from the 4s orbital is promoted to the 3d orbital. And I could do a lot of hand-waving arguments about stability and stuff, but we don't entirely know why this happens. We know that's the structure that exists in. We'll talk about that when we do PES, okay? But we just have to acknowledge that's the structure. That's it, okay? Now, I'm not going to tell you you have to memorize every single one of those, okay? They're unlikely to be asked on the AP exam, but there are about 5 elements that do that. And then for manganese, it goes right back to where we would expect it to be. Like that, and a full shell all pointed up right there. Okay, that's your little introduction to electron configurations. Now, a short little 10-second thing here. Technically, these are going to be called electron, orbital diagrams. Everybody refers to them as electron configurations, but that's their technical name. And technically, an electron configuration is a shorthand notation for how to do this. So let's talk about, say, carbon. In carbon, what we would say is that it is 1s2, 2s2, 2p2. 2 electrons in the 1s, 2 electrons in the 2s, 2 electrons in the 2p. Neon, 1s2, 2s2, 2p6. A lazier way of doing it, but it's what a lot of people do tend to use. So that's it. Technically, that's an electron configuration, and technically these are electron orbital diagrams. On my tests and on the AP exam, they are always very clear in saying something like use arrows or exponents are acceptable, letting you know what's going on, what they're looking for. Okay, thanks.